Okay, so let's start. Are there any questions for structural hazards? Are there any questions on structural hazards? Okay. Okay, so let's move on. Few of you are not here still. Right, so we've talked about that. If you're going to insert stall, then the stalled instruction is going to complete in cycle number 9, and there won't be any uh, result but in cycle number 8. So we talked about a solution for structural hazards as well just before the break. Okay, so now let's come to the next hazard, which is data hazard. Now, a data hazard is because of dependencies within the program, and you cannot write a program without dependencies in between instructions. So instructions are required to be dependent on other instructions because you need that result computed by an early instruction. And if you are just running instructions which are not taking any value from a previous instruction, then there is no use of that program. Obviously, you're going to build a program, or you're going to write a program where there is going to be some dependencies between instructions. Okay, so because of those dependencies, what happened is that a result which is computed, which is actually calculated or executed by a previous instruction, is not yet available. So for that, we are going to look at a sequence of instructions here. Here, the initial D here signifies that we are talking about double precision numbers. You can ignore this D as well. It's an add instruction, right? And it's a subtract instruction, right? So there are different types of instructions. So D is normally talking about um, a double precision operand. Okay, so what's happening in this sequence? What's happening in the sequence? So anything which is uh, common over here, or something that you feel that all these 5 instructions have? Yes, anyone? Anything unique about this sequence of 5 instructions? Anything special?
So using three registers.
Okay, so one thing is that all these instructions are using 3 registers. Anything else?
Sir, R1 is the common register used in each instruction.
Okay, yeah. So this is the main thing here that I wanted to point out, that the first instruction is producing a result R1, and all the remaining 4 are dependent on that result, right? So all of them are using R1 somewhere as their source register. So all of them are using R1 as their first source register, but it could be the second source register as well. It could have been, and say for example, instead of this value and R6, R1 R7, it could have been R1 R7 R1. In that case as well, it's the same thing, that you are using R1. So it could be on the RS side or it could be on the RT side. It doesn't matter. Both of them are the source registers codes. So the first instruction is producing some result which is used by the next 4 instruction. And the reason for selecting just 5 instruction is because our instruction pipeline has got 5 stages. Now, if it has got 5 stages, this means that any instruction which has started in the first cycle is going to move till the 5th cycle, and then you can have four more instructions in the pipeline along with this instruction. So an effect of this instruction is going to last till uh, the four cycles or the four instructions which are in the pipeline, right? So had our pipeline been of 8 cycle, we would have considered 8 instruction sequence to find out or to see what is the effect of an instruction producing a result and later instructions using that result, right? So here on we can easily see here that in this sequence we are just talking about R1 and we are not interested in other registers. So all of them are then the different registers, and we are not concentrating on R4 or R6, and we have taken all these registers are different except R1, which is common in all of them, and 5 instructions. So we are going to look at how this is going to execute. Right. So if we talk about our first instruction, add. Now um, the correct cycle where it's going to produce its result is cycle number 5, and the first half of cycle number 5 is for write operation. So it's going to write its result R1 in cycle number 5. So any instruction which is using the value of R1 should read the value of R1 after cycle number 5, or in if you keep it correctly, the second half of cycle number 5, so that it remains correct. Now let's see what's going to happen for the next 4 instructions. So the subtract is going to read the value of R1 in the third cycle. Obviously, the value read by subtract is not the value needed in this case here, because if you are depending on R1, this means you need the results of R2 plus R3, and those results are not available and would be written in the register file in the 5th cycle, and this means the subtract is fetching an older value of R1. So if we talk about AND instruction, the third instruction is going to fetch the value of R1 and R7 in the 4th cycle. Again, not possible because that value which this AND is fetching is also an older value of R1 and not the right value. So if you look at OR, now since in the 5th cycle, the first half of 5th cycle, we have written the value of R1, that's why if OR is going to fetch the value of R1, that value would be the correct value because it has already been stored in the first half of the 5th cycle and it's reading in the second half of the 5th cycle. Now this is the reason why we have writes first and reads second in the same cycle. Had the read operation been done earlier than write operation, then you would have seen that this OR is also going to have problems because it's going to read the value of R1 and then later on in the second half the correct value is going to be written. So in order to avoid that, the writes are going to happen first and then the reads to that particular register file. So that is going to make the third instruction safe, right? And similarly, if you go on to the next instruction, XOR instruction, you're going to see that the value is read in the 6th cycle. Again, not a problem because that's obviously is after the 5th cycle, and so it's not a problem in this case. So you see that any instruction which is producing a result is going to affect the next 2 instructions only. So next 2 instructions are problematic, but not the other ones. But since these instructions are somehow dependent, or maybe they are going to be dependent on each other, this means if you are going to delay the subtract and AND instruction, then you have to delay the remaining instructions as well. Any question here? Who's
Sir, Yasser.
Yeah.
Sir, can you repeat this again? Why write again? Because I joined little bit late, so unable to catch.
Okay. So
Thank you, sir.
I was saying here that there is when you're going to write to register R1, that's going to happen in the first half of the cycle number 5, right? The first half cycle number 5. But if you come to the third instruction, the 4th instruction, which is the OR instruction, It reads the value of R1 in the second half of cycle number 5. Now, since that value is written already in the register file, any read operations after that means that you're going to fetch the right value. Okay, so we couldn't fetch the right value in the first two instructions, but we had the right value of R1 in the third instruction after the add instruction, or you can say the fourth instruction. Now, since this is how we are doing it, we are doing the writes first and reads in the second half. But have we opted for reads first, and writes in the second half, then this would have mean that we are going to fetch again a wrong value of R1, because we are going to read R1 before it has been written by the add instruction. So this was my only point, that in order to have the effect of the dependencies and their effect to be minimized to as few instructions as possible, it's better to have writes first then reads. Okay, so if you're going to do writes first, then this means that any instruction which is writing to a particular register and some instruction which is going to read that register, this can work fine if it's the third instruction from that particular instruction. Now, if we have taken this particular order, reads first and writes first, then again you could have seen that this instruction is also not going to work, right? Because in that case, R1's value would have been the older value of R1, not the latest value of R1. Okay, so that's
So it means that once in cycle number 4, once the value is read, then that value will always be fetched in upcoming registers.
once in cycle number 4, you're talking about cycle number 4,
Yeah.
cycle number 5.
This is one. Sorry, cycle number 3. Cycle number 3.
Yeah, in cycle number 3, then
No. Sorry. Yeah. Cycle
5.
number 5.
Yeah,
Five.
yeah. In cycle number 5, then what happened?
You mean that once it is read, then it is on carry. It will carry on the same value in upcoming registers.
When it has been written, not read. Once it has been written, then any other instruction which is going to use the value of R1 is going to read it from the register file directly. That's okay. So it's waiting for the write operations to happen. So that's the blue line showing over here. When is it actually going to be written? So the result is going to be written in the 5th cycle. And where do we need that result? We are fetching it in the 3rd cycle, the second half of 3rd cycle, or the second half of 4th cycle. Now both these two operations are earlier than the correct value which has been written in the first half of 5th cycle. But this operation which is happening in the second half of the 5th cycle is okay, because the value has already been written to the register file, and that's why we can obviously have this value available to us, right?
Okay, sir.
Okay.
Got it.
So again, coming to the sequence here, what I was saying was that if an instruction is producing a result and that instruction is an add instruction, then next two instructions which are dependent on it cannot start at the right time, because they don't have the value with them, right? But the 3rd and the 4th instruction can continue, because they are going to fetch the right value, right? But if we are going to run this program, and this program is to be run in the same order, then obviously if we are going to delay subtract, then we are also going to delay and we are also going to delay OR and XOR. So OR and XOR cannot start from this point, because subtract has to happen first. So subtract cannot start from this point. Subtract cannot start from this point, because you know that if there is some instruction producing a result, then there should be a difference of 2 cycles between that instruction and any other instruction using that result. So if you need to subtract to use that result, it should be aligned with the 5th cycle, where the first instruction is going to write the register to the register file, and that instruction is going to read from that. Anything before that is not acceptable. Okay, so if you need to execute subtract right after add, then subtract should start from this position, and should start from this position, and or should start later on, XOR even later, right? So this means that nothing is going to happen in these two cycles. So nothing is going to happen in these two cycles. This means we have wasted two cycles. And if we have wasted two cycles, our CPI is obviously going to increase, because you're not going to get any result in cycle number 6 or cycle number 7, right? So again, this is one way to do that. If there are dependencies in the program, what you can do, or what the compiler can do, is before that program is run, the compiler can insert no operation instructions in between the codes, in between the instructions of the code. So if the compiler sees this particular code, and the compiler knows that an instruction which is producing a result and any subsequent instruction which is using it needs to have two instruction gap in between them. So what the compiler is going to do is it's going to have two more instructions, two more no operation instructions in between add and subtract. So this instruction is going to be then a no operation instruction, this is no operation instruction, and this would be your subtract instruction. But this is not the right way. This is not a good way, because you're going to waste two cycles here. Okay, so you can do that at compile time. You can do that at hardware level as well. The easier part is the compiler way. I'm going to come to the hardware method. How can we insert stall? But if you need to insert stall, if you need to have some delay in between instruction, compilers can also do that. And then they just need to have a sequence, and they just need to know when and how much to insert. So they need to know that the sequences that the destination code of the previous instruction, if it matches with the source code of the next instruction, and it's such an instruction which is writing to a register file, then this means that there is going to be a problem and you cannot continue. So you have to insert two no operation instructions in between. So that's one solution. That's one solution, that you can have two no operation instructions in between, right? Okay, but that's not a good solution. That's not a good solution. So we have discussed about that, and this is again something which I've written with what we have just talked about. So one way to solve it is to delay the subtract instruction. If you are going to delay subtract instruction and is also delayed, so you just have to insert two stalls, and everything is then going to go fine. Because if you're going to insert two stalls, then subtract is actually going to start from this point onwards here, and is going to get the value over here, and OR is going to get the value in the 7th cycle, and XOR is going to get the value in the 8th cycle. So everyone is getting the value after it has been written, and that's fine, right? But we also are inserting two stall cycles. Now, if you closely look at the sequence, I'm going to come back to that particular slide, because this has a bigger picture. So what is the problem in this case? The problem is we are writing to R1 very late, and we need it earlier. Okay. So can't we stretch that thing from both sides? Stretching means that do we really need, do we really have this value only in the 5th cycle? Or in other words, are we really getting this value only from the register file? Are we really interested in the R1? Or are we interested in the result? So that's the question. So do we have to read the register file? Our register contains R1, or are we interested in the result R2 plus R3 to proceed? So the answer is we need the result. We are not really interested in reading the registers. We are interested in its result, If we have this result, then we can continue with the subtract operation. The only thing is somehow we can give this result to the subtract instruction. Now, if you look over here, how early as possible are we getting this result? So if you look over here, the earliest possible time is that result would be available at the end of third cycle. So you have this value of R2 plus R3 stored in this register at this point of time. Okay, so at the beginning of fourth cycle, you will have this value with you. So if somehow you can provide this value from this particular register, this is actually, this stage is EX stage, and this is the MEM stage. So we are going to call this register as EX/MEM pipeline register. So this register is actually EX/MEM pipeline register. And we had this convention in the last class that any register which is separating two particular stages would be named after the stage previous to it and the stage next to it. And then we are going to call this register as EX/MEM pipeline register. So if we can have a method to provide the value directly from this register to any unit that needs it. Okay, then where do we need this value for the next instruction, subtract instruction? So actually we are reading the value here in the third cycle. Again, that's not going to work, because if we need this value in the third cycle, that value is not available till the end of third cycle. So if you need that even in the third cycle, you cannot do anything about that. So then we ask another question: how late as possible do we need this value? Right? How late as possible do we actually need this value? Because in this particular stage, we are reading the contents of we are reading the register file and the contents of R1. But now we are talking about a different thing. We are talking about not R1, but we are really interested in the result of the previous instruction, which is R2 plus R3. So how late as possible do we need that? So we see that this result would be utilized in the execution stage and never before that. So you are going to use that value in the execution stage. So if you need that execution value in the execution stage, which is happening in the fourth cycle, so you need some mechanism over here which can pass on the value from EX/MEM pipeline register to ALU somehow. Okay, so if we have got some path here that can do this for us, then maybe we can think about executing subtract from its right cycle, which is the second cycle. So is everyone getting this? So normally there is a problem, because normally we are going to write the results in a register file and read only from register files. But now let's talk about some different solutions. So our solution is, are we really interested in reading and writing from the register file, or can we think about getting the results earlier and providing the results to the particular modules earlier or later in time? So if that is the case, then we can think about some other solution. So the first thing is, we are not really interested in reading R1. We are interested in its value, and if we can get this value from the pipeline earlier than the fifth cycle, that would be good for us, because that value is provided earlier to us and we can think about executing at the right time. Then for the second instruction, what we see here is how late as possible do we need it, because if there is a combination which can match and you are getting the result earlier than that, then obviously you need to just pass on that value to that particular module. So we see here in this example that R2 plus R3 is available by the end of third cycle, and we need it at the start of fourth cycle. So now you can think that this makes sense, that third cycle and then the fourth cycle. So it's never about getting it before time. So you are talking about getting it after that particular time, after that result has been computed. Now the only thing that we need is, we need to have some paths like the paths that we are shown over here. So we need some paths, And obviously, since now the ALU is getting two different inputs, we need some selection circuitry as well, which is going to select either that input is going to come from the register file or that input is going to come from some pipeline register. Okay, so if this is the case, then we can handle that using a different scheme. Okay, so we call this scheme as forwarding, right? So forwarding is a way, or is a technique where you are going to pass on the value uh, from the module which has produced the result directly to the functional unit that requires it, right? So we've talked about that in the previous example, that result is not needed until the ALU stage, and then if you can provide that result, then these two instructions can continue in subsequent cycles, right? So if you look over here, uh, what we need is to pass on the value from EXMEM pipeline stage back to ALU. Now remember, I have drawn the five stages again and again. They are just five stages. Okay, they are just five stages. It's just drawn for clarity that how you can see which stage is utilized by a particular instruction at a particular clock cycle. What normally we have is what actually we have is only these five stages. Okay, so they're just drawn and drawn multiple times, but there is just one set of 5 units. So what we are talking about is getting the result from this pipeline register back to ALU. Okay, so this is the main thing that we are talking about, is getting the result from the pipeline register back to ALU. Okay, in other words, what's shown over here is we need to pass on this value to ALU. Any of these inputs doesn't matter, because it depends on where you're utilizing that. If it's on the RS side, you have to provide it from the RS side. If it's used in the RT side, you have to provide that result to the RT side. Okay, so this result there should be a path which can provide the result from this pipeline register to any of the inputs of ALU. But ALU already had some inputs coming from earlier stage. So obviously you cannot give a single, you cannot give two different inputs to the same input to the same port. So there is a single port over here. You cannot attach two different inputs to that port. So what you have to do is then think about using a multiplexer. So if this is your ALU, then what we can do is have a multiplexer over here, which is going to give one input to the ALU, right? And one of the inputs is normally coming from the register file, which is still going to be there. And the other input is coming from the EX pipeline register, which is a new one. And we need to give that as a second input to the multiplexer. Now, whenever there is a multiplexer, so there are going to be some select lines to choose the right input. So there are some select lines as well to this multiplexer. If there are just two inputs, you just need a single bit select line to select either a 0 value or a 1 value. But the question is not 0 or 1. The question is who is then going to give this select signal, right? So if we talked about reducing the stalls for data hazards, and we said that we can manage that by forwarding. Now in the technique of forwarding, we pass the result from a pipeline register to the functional unit that needs it. And for that, we need two things. We need a path which can provide the result. And we also need a control unit which can select these signals for the multiplexer. We call this control unit, we call this data circuit as forwarding unit. So this is a forwarding unit. So technique is called forwarding, and these units are called as forwarding units. So I cannot write that correctly over here, but yeah, these are units are called then forwarding units. So the task of forwarding unit is to generate the select inputs for these multiplexers. Okay, so that's the only task of the forwarding unit. And how it's going to do that, we are going to come to that shortly. Now we have discussed about subtract. So subtract can move on, right? So subtract can move on because if we have this path and if we have some forwarding unit which can select the right inputs to go to the ALU, then our problem is solved. Okay. But then let's come to the AND instruction, because we know OR and XOR were already fine. Let's come to the AND instruction. Now, if you come to the AND instruction, we see here that the same logic that we did earlier, that result is available at the end of third cycle. The result R2 plus R3 is over here. Okay. And where do we need that? So we need that in the fifth cycle here. Okay, so we need that. If you talk about AND instruction, the result of R1 is required for ANDing with R7, and that's going to happen in the execution stage. So we need that at the beginning of fifth cycle, right? So we don't really need that in the fourth cycle where it's going to read the value of R1. No, we are now going to use, we are going to see how, where are we going to use that value. So we see that this value is required in the fifth cycle. Again, it makes sense because that you already have that result in the third cycle. And if you need that in a later cycle, that is still possible. But nothing before that is possible. But what's going to happen over here? Now, this register was EX-MEM pipeline register. But after one cycle, that result would have moved to the MEMWB pipeline register, because this is the register which is eventually going to write that result to the register file in the first half of fifth cycle. But we need that before the first half of fifth cycle, remember. So we need that in the beginning of fifth cycle. We can't wait for the result to be written over here and then fetch it from the register file. No, that cannot happen for the AND instruction. So we need that result in the beginning of fifth cycle. So in this case that we have discussed, we said that that result is coming from EX-MEM pipeline register. But if we are going to talk about EX-MEM pipeline register, that register is this register, in the beginning of fifth cycle. So in other words, what we are talking about is getting a result from this particular register to ALU. But that register, but this EX-MEM pipeline register is now holding R4, or not R4, R1 minus R5's value. Or in other words, R2 plus R3 minus R5 value. But we don't have to work on this value for the AND instruction. So this is the value which is currently over here at the end of fourth cycle. But we don't need this value. We need R2 plus R3's value, which is over here in, not in EX-MEM pipeline register, but MEMWB pipeline register. Okay. So this value is available in MEM because this stage is MEM stage and this stage is the write back stage. So this register would be called as the MEM/WB pipeline register. So we have this value that we need for R1 not in EX-MEM pipeline register, rather MEMWB pipeline register. So, and if we need to forward this value also to the ALU, this means that this ALU should not have just two paths but three paths. One coming from the register file, another coming from EX-MEM pipeline register, and another coming from MEMWB pipeline register. So there should be three paths, and the forwarding unit's task is to select between any one of them. Now, if this is the case that you have three paths coming to the ALU and the forwarding unit is going to select the right path either from the register file or from the EX-MEM pipeline register or from the MEMW pipeline register, then you can also execute the AND instruction correctly, right? And OR and XOR were already fine, so they can continue on because you have not delayed any instruction. So this is how you can remove the stalls from the sequence of these five instructions, right? So any question up till now? Except that we haven't decided how it's going to be done. We haven't decided how it's going to be done. That how is the forwarding unit going to know which particular input should go to the ALU? That's the main question. But what we have discussed up to now is if we have paths coming on from some pipeline register back to ALU and there is a multiplexer and then there is a unit which is responsible for selecting the right inputs, then our problem can be solved. The only question is how would this forwarding unit know which inputs to select, right? So that's the next question which we are going to come now. So where to find the ALU result? So we have already talked about that. So we can get this result from EXMEM pipeline stage or MENWB pipeline stage, right? So how is the forwarding unit going to select the correct inputs to the ALU? Now, if there is no hazard, if there is no dependency, then the ALU operand will normally come from the register file just like before. Okay. Now, if there is a hazard, the operand will come from either the EXMEM pipeline register or MENWB pipeline register, right? Depending on where that particular value currently is, right? So for that, we need two different multiplexers for both the inputs of the ALU, and we need a unit which we are going to call as the forwarding unit, which is responsible for generating the control signals, right? So if you come to the whole diagram, this is the data path. I've still not discussed how is it going to be happening, how is the forwarding unit going to work. So, but this is the complete diagram. I'm going to discuss about that. So uh, this forwarding unit has also got some inputs coming in from different other registers. That is important thing which we have not yet discussed. But if you ignore that inputs coming to the forwarding unit, you know that this forwarding unit is responsible for selecting the correct inputs. And if you look at the dark red lines, these are the forwarding paths. So one of the path is coming from EXMEM pipeline register, and that's going back to the second input. So it's attached to the second input of both these multiplexers. Okay, so that's one thing. And then you have your second input coming from this multiplexer, which is the result after the MENW pipeline register, and it's going to the first input. So that's your third input to the multiplexer, and this is your normal input, which was directly connected initially to the ALU's first input, but we have now introduced a multiplexer, another multiplexer to the second input of the multiplexer to the ALU, which already had a multiplexer which was controlled to select between the register or immediate contents. So that's going to be still there. We are just talking about the register contents over here. So we are going to have another multiplexer over here and select the right register content, right? So this is how we are going to do this. But how is this forwarding unit going to work? Okay, how is this forwarding unit going to? So if there are any question up till now, you can ask me. If there is something you need to discuss as well, I'm now going to come to how is this forwarding unit going to decide which input should go to the ALU. Okay, so if there are no further questions, then let's talk about our first forwarding, which we are going to call as ALU to ALU forwarding, which we said that if this is the ALU and this is the pipeline register, which is the EXMEM pipeline register. So if you have result computed from the ALU and you want the same result to be part of the next operation, then we call this an ALU to ALU forwarding, or in other words, EXMEM the better word is the EXMEM pipeline register to ALU forwarding. So since we are forwarding it from the EXMEM pipeline register back to ALU, that's a much better word. Okay, but the main thing is the ALU has computed something and you want that same thing for the next instruction. Okay, and this is the condition. The previous instruction will write to the register file and the previous and destination one of ALU source register in EX state. Now I'm going to come to the example first. How are we going to decide? So I'm going to take some example here. So I'm going to write over here and then I'm going to rub. Okay, so I'm going to take, say, another example. Add R1, R2, R3, right? And subtract R4, R5, R6. Okay, so what about this sequence? How am I going to move? Is there going to be a data hazard over here? Anyone?
No, sir. It will
No.
not be.
No, because there is no dependency. You can see here subtract is not depending on its result from add instruction, so it's waiting for it's using R5 and R6, and these results are already there in the register file, so it's going to move. There is no problem in this way. So what I need to do is now I'm going to change this R5 to R1. Now there's a problem over here, the same problem that we have discussed. But we see here that the the value, the add instruction is going to move to the memory stage when the subtract instruction is going to come to the execution stage. So we need the result of R1, R2 plus R3, which is over here in the EXMEM pipeline stage, and we need that result to be part of our next instruction. So when add moves to the memory stage, subtract would be there in the execution stage, right? So add is in the memory stage, but subtract would be in the execution stage, and here we need this value of R1, which is not the correct value coming from the register file. So we need this value EXMEM. Now, how are you then going to decide that it should come from EXMEM pipeline register? Okay, so what you need to see here is the previous instruction should have a matching destination and source of the next one. Okay, so if that is the case, then the forwarding unit should provide the data from the pipeline register, not from the register file. Okay, now how are we going to then name these registers or the control signals if they are required? So for that we are going to use a convention, and that convention is that any instruction which is moved to a particular stage, all the control signals and all the register codes also move with that particular instruction. So if add is over here, all its register codes like R2, R3 and R1 also go with that same instruction. And if it's utilized, then it's not forwarded anymore. But if it's not propagated anymore, but if it's not utilized, then it moves with that particular instruction wherever that instruction goes, whichever stage that instruction goes. So since in the memory stage, the next stage would be the write back stage, and in the write back stage, the add is all going to write the data in R1 register. So this means that the code of R1 is going along with add, because it would eventually be used in the write back stage. So that code is also over here in the pipeline register, and it's also going to be over here in this pipeline register. But then there should be some convention to address this code, to name this code. So that convention is that we are going to write this register code for that particular instruction by the name of that particular pipeline register currently holding that code, and that register that we are talking about. So if you're talking about R1's code, that's currently over here in EX MEM pipeline register. So we are going to call that code as EX/MEM dot register RD. So I'm writing the short form over here. I could have written the whole register name, but EXMEM register RD means that I'm referring to the RD's code, the destination code of the instruction, which is currently in the memory stage. Now, if I talk about IDEX dot register RD, that is the destination code of the instruction which is currently in the execution stage. Okay, so if my forwarding unit is somewhere here in the execution stage and I am talking about these two register codes, then one of them is referring to R4 and the other one is referring to R1. So this one is referring to R1 and this one is referring to R4, because the instruction which is currently in the execution stage is the subtract instruction and its destination is R4. So that code is actually R4. And this instruction which is currently in memory at this point of time, that instruction is add instruction and its destination code is R1. So it's going to return R1. Okay. So if you have this convention in your mind, then the only thing that we need to check in order to know whether to forward or not to forward is that RDs of the previous one should match RS or RT of the instruction which is currently in the execution stage. Okay. So I'm going to clear this here. Okay. Now, so once we have this, so I'm going to just come to the conclusion. Now, this is the sequence that we have to check. The main thing over here is this. Remember, in an ALU, there are two different inputs. So we are just talking about the first input. We are just talking about the first multiplexer. So it's getting one value from the register file, another from EXMEM pipeline register, and another from MEM WB pipeline register. So currently we are not talking about MEM WB pipeline register. We are just talking about, oh sorry. Currently we are talking about just getting inputs from EXMEM pipeline register and selecting between the normal register and EXMEM pipeline register. Okay, and we are talking about the first input. So for that we have a signal which we are going to call as forward A. So we have this signal as forward A, and the second one as the second multiplexer will have its own signal which we are going to call as forward B. Okay, so we are currently talking about forward A, and we have these two inputs. So what we have to see is normally that was the content of RS that were coming from the register file. But now we have another input which is coming from EXMEM. And we are going to decide when are we going to use this content from EXMEM to ALU. So we need to check that the destination code of the instruction which is in the memory stage should match the source code of the instruction which is in the execution stage. So if they both are matching, and that instruction which is in the memory stage is also going to write to the register file. Now it can happen that these register code can match, but the previous instruction is not an add instruction, rather it's a branch instruction, and branch instruction don't write to any register, and you don't need to forward anything in that case. So in order to avoid the branch instructions then we have explicitly mentioned that that instruction, the first instruction or the instruction which is producing the result, should be an instruction which is going to write to the register. And this is an example of using the control signals. So we're talking about the control signal read register write for the instruction which is currently in the memory stage. Okay. Now, if both of these conditions are true, then you have to forward the value from EXMEM pipeline register. This is according to the um, to the picture over here, to the example that we have shown over here, because 2 is coming from EXMEM pipeline register back to ALU. So we have selected the value 2 because we need to forward, if we need to forward from this case to ALU, then that's the case that we have to generate the value of 2 over here. So if they both are matching, if the source register and destination registers are matching, then you have to forward 2. Now this was for the first pipeline, if this was for the first input. Similarly for the second input, you can do the same thing, but instead of RS, then there would be RT. Because in that case, the normal input was the contents of RT. And so we are going to forward this value of RT or the value coming from EXMEM pipeline register to the second input of ALU. If this matches, that is, that the instruction which is currently in the memory stage has a destination register code which matches with RT code, and that register, that instruction which is in the memory stage is also writing to the register. So there shouldn't be any store or branch instruction. Then in that case, we have to forward the value of 2. Again, the 2 value is coming from that same same diagram that we discussed. Again, in both these multiplexers, the 2 value is actually from the EXMEM pipeline register back to the ALU. Okay. This was about ALU to ALU forwarding. Now, if we have to do or in other words, EXMEM to EX/MEM to ALU forwarding. Now, if you have to do from MEMWB to ALU forwarding, what is the condition in that case? So, if you have to do MEM to ALU forwarding, then you have to see that the previous instruction again is an instruction which is writing to the file, register file. The previous instruction shouldn't be that previous instruction, or in other words, 2 cycles ago. So we have talked about 2 cycles ago. So that previous instruction is writing to register file, and the destination is one of the ALU source register in the execution stage, right? And the condition for that is this one. So I leave this as an exercise. You can do that yourself as well. The main thing that you have to see is the instruction has moved to the write back stage, and the current instruction is still in the execution stage. So you need to check the instruction which has moved to write back stage has a matching destination code with the source code of the instruction which is currently in the execution stage, and this instruction which is in the write back stage is writing to the register file. So if these two conditions are true, then you have to forward the value coming from MEMWB pipeline to ALU. Sometimes it's called as MEM to ALU forwarding. Now this is an additional condition which is written over here, and if you're going to see, this is actually the inverse of this whole thing which is written over here, which is actually the inverted form of this. And I'm going to ask you why is that in the next class. So you have to read about that as well. Why have we written this over here? There is a case why we have written this. So I'm going to leave this, and I'm going to ask you. So this was for the first input, and if you're talking about the second input, then instead of RS, we are matching the RT with RD, and also the inverted form of RT in this case. Okay. And if this is the case, then we, in both these cases, we are forwarding the 1 value, not the 2 value. So previously we were forwarding the 2 value over here. Now we are going to forward the 1 value, which is actually coming from MEMWB pipeline register back to ALU. Okay, so this was about data hazards. This was about data hazards and the forwarding unit. So if you know that you have to actually find out these conditions, all of these. This is the main thing. These conditions and the one in the previous slide, these conditions. So if you're going to design the forwarding unit, what you have to do is then pass on these values to the forwarding unit, and internally in the forwarding unit, you are then going to have some comparators which are going to check the code. So I'm going to take one example over here. So this is the whole diagram, the forwarding unit, but I'm just going to take one example. Like we are matching in this sequence. I'm going to drop this as well. In this sequence, what we are doing is we are matching the code of exmem.register rd with idex.register rs. So where are we going to find exmem.register rd? So we are going to find this value over here. exmem.register rd is actually coming at this point of time. So what we do is tap this value, this 5-bit code, and pass it on to the forwarding unit. Okay, and we are matching it with uh, idex.register.rs. So we are going to get idex. So IDEX is over here, and IDX.register.rs is this value which is coming from this point. So we are going to give this value to the forwarding unit. So we are going to put this value and this value, and internally there is going to be a comparator which is just going to check whether these two are same or not. Okay. Similarly, what else do we need? We need EXMEM to register right. And where do we have this value? We have this value in EXMEM pipeline register. So that control signal, that register write control signal is also provided to the forwarding unit. Now this was for the first condition here, and for the second condition we have the only thing different in this one is the RT. So we are also providing RT contents here to the forwarding unit. So internally there would be another comparator which is going to compare RT value and RD value together. Okay, so I'm not talking about the internals of forwarding unit because that can be implemented in different ways and that's not part of our course. So the main thing is we are going to just describe it in terms of conditions that are needed to be checked. So these conditions are needed to be checked that we have discussed over here in the slide number 15 and 16. Uh, these all of these conditions. Okay, and I leave this as an exercise for you to know why have we inverted the first condition and added it as an and to the second condition. Okay, right. Any question up till now? Because this data hazard is a big topic and I need to finish it in this class. If there are any problems, then because this is the first time you are going through the pipeline hazards, and this is the first time you have introduced you are introduced the concept of forwarding in for most of you, and not all of you. So if there are any problems, then you can ask your questions. Is everything okay? Okay. So if everything is okay, who is this? Akash Ali, do you need?
Yes, sir.
Yeah. Do you need to ask something?
No, sir.
Okay. So let's move on. So let's come to another example over here. Now in this example, there is a store instruction which is using that result um, of R1, and it's also using the result of the previous instruction load. Okay. So, and this is a diagram showing if we have a forwarding unit, how the thing's going to move. So add is producing a result R1, which is used by load in its execution stage. Then load is producing a result R4, which is used by store, and store is also using R1. And this is the whole diagram over here. So add is producing a result, and that would be available at the end of third cycle. This one R1. Okay, load needs that result in its execution state, so it has that. It would be forwarded, and we have just talked about the EXMEM pipeline forwarding for this case, right? So that's okay, and nothing more required for load. So let's move on. For the store, now store needs the value of R1 and the value of R4 as well, but these two are used at different point of time. Like for example, in the execution stage, store needs just R1, and in the memory stage, then store needs the value of R4. So let's talk about where do we need. We have this memory stage, this execution stage over here, and that result of R1 would have it would have moved to the MEMWE pipeline register, and so you can forward from MEMWE pipeline back to ALU, and send. This is okay, right? Now this is a new thing here. This is a new thing here. Store load producing a result and store using that result, so in its memory state, because store has got two source registers, and they are used at different points. Normally, if there are two source registers, they are used both in execution unit. But in store, what happens is one of them is used in the execution unit, the other one is used in the memory stage. So that's the other one, R4, and that's used in the memory stage, right? So again, that but R4 is read in the decode state over here. So if you're going to read R4 value over here, that value is not the right value, because R4 is going to be loaded from memory, and the earliest possible time that you can get this value is at the end of fifth cycle. Actually, you're going to store that value in the first half of sixth cycle, and if you need to read the correct value from the register file, then that second store should be aligned with this write operation, and so you need again 2 cycle stalls, and that store should be starting in the fifth cycle, so that the register read operation happen in the second half of the sixth cycle, right? That's the normal position if you don't have any forwarding paths. But if you have any forwarding path, now this is the third forwarding path, because previous to that we have always talked about forwarding from a pipeline register to ALU. Now here we see that we don't need the input to the ALU. We are talking about getting that input and providing it to the memory stage. So what we need is the MEMWB pipeline register providing the result to memory stage, to the memory. Previously we had EXMEM to ALU and MEMWB to ALU. Now we are talking about an MEMWB to memory. Okay, so we need a third type of forwarding path and another forwarding unit, because the previous forwarding unit was working in the execution stage. Here we need a forwarding unit which should work in the memory stage. Okay, so if that is the case, we need another forwarding unit. Along with that, we need a forwarding path from MEMWB pipeline register back to memory. Because this memory stage is only used by store instruction, that special sequence is only applicable whenever you have a store instruction in your code. Okay, and which is using the value of any previous instruction. So it's not necessary that it could it's a load instruction. It could be an add instruction as well. And I leave that as an exercise. You can do this also for add instruction, where the main thing is that store is using that result in this memory stage, not in the execution stage. Because if it's using in the execution stage, we have already talked about those forwarding paths. So this is the third path again, which is something that you can do it yourself. So I'm going to skip that. You can find the conditions for that path, for that condition, for this particular case. Now let's move on to our last example of data hazard. This is another sequence where we have a load producing a result rather than an arithmetic instruction. So that the only difference from our first example is that instead of an add instruction, there is a load instruction producing a result. And we have talked about 3 instructions more that are used. We could have talked about the 4th instruction as well, but even 3 instructions are going to be fine to see the effect. As we have talked about that the effect is going to come to the next 2 instructions. For arithmetic instruction, let's talk about how is it going to affect the load producing a result. Now what's different in load? The difference here is that we get this value even later. So if you're talking about an R type instruction, you get this value at the end of 3rd cycle. But when you're talking about a load instruction, that value is there at the end of 4th cycle and not before that, right? So if we now talk about the next instruction, which is subtract instruction, then we ask us the same question, because we know that subtract is going to read the value of R1 in the decode stage, and load is going to write that in the last stage, which is the 5th cycle. So that's not possible. So then we try to stretch it from both ends. We try to see how early as possible can we get this value and how late as possible do we need it. So if you talk about load, the earliest possible that you can get this value is at the end of 4th cycle. And where do we need this? So the latest possible here is the beginning of 4th cycle, because we need that in the ALU stage. Now the result is there at the end of 4th cycle. We need that at the beginning of 4th cycle. This means even with forwarding, you cannot do this, because there is no way to get this data before time, because that data is going to be available at the end of 4th cycle, and we need it at the beginning of 4th cycle. Not possible, right? So this sequence is a unique sequence which cannot move without inserting a stall. And since this sequence involves a load instruction producing a result, we call this hazard as a load use hazard, right? We call this as a load use hazard, meaning that load is going to produce and some other instruction is going to use that result in its execution state. Now this is implicit in here, that the next instruction is using it in its execution state, because in the previous example we just saw that load was using a result, producing a result, and store was using it in its memory state, and there was nothing, there was no problem if we had MEMWB to memory forwarding path. But in this case, if the result is used in the execution stage, forwarding cannot help you, because you don't have that value till the end of 4th cycle, and you need it at the beginning of 4th cycle. Now if you talk about AND instruction, that value can be provided if we have an MEM to ALU, MEMWB to ALU forwarding, and we have just talked about MEMWB to ALU forwarding. So we have already that forwarding path. So if that forwarding path is available, this AND can proceed, and this OR can obviously proceed, because it can get that data directly from the register file. So that's okay, but this instruction is not okay. And if these 3 instructions have to happen in the same order, then if you have to delay subtract, then add and OR are automatically delayed as well, right? So this is an example of a load use hazard. This is an example of a load use hazard. Okay, so what to do in this case? Now in this case we have to insert a stall, and in order to insert a stall, there can be 2 different techniques for that. One technique that, as I've mentioned earlier, is an easier one, which is the compiler based technique. So compiler is going to look at sequences from a code. So once you have written your code, the compiler is then going to check that code for this sequence where there is a load instruction having a matching destination with some and with the next instruction source registers. So if the destination source register codes are matching, then the compiler is automatically going to insert a no operation instruction, an additional instruction in your code, which is going to solve the problem, because now this instruction becomes a no operation instruction, and subtract actually starts from this point of time. So it's going to increase the CPI, also result in lower cache hits because of more no operation instructions. So, but the subtract is then going to have its ALU in the fifth cycle, and that result can be forwarded using MEMWB to ALU forwarding, and then the subtract can move, and then the subtract can go fine. So, but the compiler has automatically inserted one instruction between that. Okay, but this can also happen using a hardware unit which decides on runtime when to insert a stall and when not to insert a stall, and how to insert a stall, right? So we are going to talk about that. So if you have got a hardware unit doing the same task, that hardware unit is also sometimes called as a pipeline interlock. Okay, so when MIPS was initially designed, this acronym standard for microprocessor without interlock pipeline stages. That is, this microprocessor was designed without considering this hazard detection unit, and everything should every thing like insertion of hazard was required to be done at compile time, not at runtime. But later on, when they saw that this is affecting the performance, so they introduced a hazard detection unit, but did not change their acronym. So today, still MIPS stands for microprocessor without interlock pipeline stages. This is not millions of instructions per second. That's another term. But this MIPS processor stands for microprocessor without interlock pipeline stages. And the acronym wasn't changed after the introduction of hazard detection unit, right? So it's the same acronym MIPS, standing for microprocessor without interlock pipeline stages, but it has got a hazard detection unit which can decide at hardware level at runtime whether or not to insert a stall. Okay, so I'm going to come to an example over here. So if we need to insert stall, again we need to decide and check for some register codes that are matching, right? The first thing that we need is that the first instruction should be a load instruction. So that's our main condition. And the second thing that we have to find out is the next instruction is using the result of that instruction, like this case here. Now, if we decide that over here at this point of time, if we decided over here where the subtract has moved to the decode stage and load has moved to the, or can we decide it over here, or should we decide it over here? So this is the next question. How early can we decide to insert stall? Now, if we are going to decide to insert stall, this means that anything in the pipeline also has to be removed. So this means it's good if we do it early. So we try to see whether we can do that in the first cycle. So we cannot do it in the first cycle because the second instruction is not available over here. So we don't know, and we also don't know whether it's a load instruction in the first cycle. Now, can we do it over here? Now, again, we cannot do it over here because we don't know, first of all, whether the first instruction is a load instruction because it's not decoded yet. Secondly, the subtract instruction is fetched in the second cycle, and we don't have the register codes. We are going to have the register codes after it has been fetched. So we need to check the register code. So that's not possible over here as well. So can we do it over here in the third cycle? Yes, we can do it in the third cycle because load would have moved to the execution state, and by that time you have the control signals available. So you know that whether the instruction in the execution stage is a load or not, and you in the decode stage you also have the source register codes as well available with you. So this is the right time to do it. But the problem is by that time one more instruction is fetched and is already there in the pipeline. Okay, so if you are going to insert stall, you have to repeat some procedures again. Okay, so I'm going to do that once more. So this is the right time to detect whether we have to insert stall or not. And if we are going to insert a stall in the third cycle, and instruction has already come into the pipeline, so if we need to insert a stall, we need to decode the subtract instruction again, right? Because we are inserting a stall, we have to nullify this subtract and do the subtract operation again. So this means that this decode has to happen in the fourth cycle again. So nothing is going to happen for the remaining stages. This subtract actually is the next instruction, and becomes the very next instruction. So everything moves on one cycle below, right? So how is this going to happen? And if we have decoded and we have found out that we need to insert stall, then what are the actions required at the hardware level? And if an instruction is fetched, we have to fetch that again. Okay. So how does this happen? This happens by just doing three operations. The first operation is to freeze the IFID pipeline register. Okay, so that's the register which is holding the instruction over here, which is subtract instruction currently for the third cycle. Now, if we freeze this pipeline register, it's still going to hold the 32 bits of subtract. So in the next cycle, this instruction is still going to hold subtract instruction, and you are going to decode subtract again. So this is the decoding of subtract again, right? And if you're going to decode subtract again, all the remaining operations are going to be for subtract. So this is the first thing that you have to do, that is to freeze the IFID pipeline register. I have written the steps in the next slide. I'm just discussing it over here. Now, if you're going to freeze the IFID pipeline register, that this means that anything which is fetched in the third cycle cannot be stored in that particular register. So if you have fetched the AND instruction and you cannot store that 32 bits, this means all these values are wasted, and then you have to repeat that procedure again. Now, in order to repeat that procedure again, we also store the program counter's value. We also freeze the program counter value. So the same program counter value is going to be there in the fourth cycle, and if it's pointing to AND in this point in the third cycle, and we have frozen that value, it's still going to point to AND in the fourth cycle, and this means that it's again going to fetch the AND instruction, which means that this instruction then becomes the AND instruction. The third thing, the remaining thing left, is that since we have decoded this instruction and this was a subtract instruction and we don't want anything related to subtract to continue, so we need all the control signals to be nullified. So instead of giving proper control signal for subtract, we are going to give 0 as control signals, and this 0 means that the next stages are not going to do anything. Now, this is how a stall happens at runtime. We do three things. We freeze the IFID pipeline register, we freeze the program counter value, and we give 0 control signal in that particular cycle. Now, if we do these three things, then automatically there is a difference of one instruction in between the load and its use. Now, all of this is described over here. These are the conditions that are needed to be detected. So for a load use hazard to happen, the first instruction should be load. And since we are talking about doing that in the decode stage, this means this is the time where you are going to do that. So the load has moved to the execution stage. So its control signals are here in the IDEX pipeline register. So what we are checking is IDEX.memory read should be 1. This is only 1 for load instructions. So this is the condition to check this case here. And then we are checking whether there are matching register codes. So we are checking whether the value of destination register. So at this point of time, the destination code is in RT's is in RT. After this point of time, it moves to RD. This is because of the multiplexer which is over here. Um, so we are checking whether RT is matching with the source code of the instruction which is currently in the decode stage. So if this is true or this is true, then we have to insert stall. And how do we do that? We do that by doing three things. The first thing is we don't write anything to the IFID pipeline register. That is, this input is disabled. The second thing is we don't do any write operations for program counter, which means that PC write value is also disabled. The third thing is we make all the control signals 0, right? And if you look at the condition that we have discussed just in the previous slide, you can see that we have provided the right inputs to the hazard detection unit. Again, a simple circuit, which is just comparing the values of registers and OR in an OR gate and an AND gate and some control signal checking. So we are providing it with a memory read signal and some destination register codes. So you see here that the memory read signal is going to it and some register codes are provided, the RT code and the RS and RT codes coming from this instruction. So internally what's happening, we are not concerned with that, but this hazard detection unit is going to give three outputs. One is it's going to disable the IFID changes, disable the program counter changes, and make all the control signals 0. And this is how you are going to insert a stall at runtime. So I'm going to stop over here. So today what we have discussed, so next topic is the control hazard, but I'm going to stop over here. So what we have discussed today is pipeline hazards, and pipeline hazards we discussed about structural hazards and data hazards. So structural hazards were easy. Structural hazards are the only hazard that can be eliminated completely, because if you can replicate the resources, the hardware resources, then you can remove the structural hazard. You don't need to insert any stall. Then we talk about data hazard, and we talk about a technique called forwarding. So forwarding is helpful, but for forwarding we need two things. We need forwarding paths and we need a forwarding unit, right? So if we have both these things, and for forwarding unit we have internal we condition to satisfy which inputs are going to go on to the required unit. So we can use forwarding for ALU. We can also use forwarding for memory. So we discussed about that. Then we discussed about another sequence where forwarding is also not going to help, and that is called as a load use hazard. And whenever there is such a case, there can be two schemes to handle it. When one scheme is at compile time, so a compiler can insert extra instructions, or you can do it at runtime. And for if you want to do it at runtime, you need a special unit called a hazard detection unit to be inserted in your code, and that unit is responsible for doing three things: to disable that particular instruction to move forward, and repeat the decode and fetching operations that have been done for the next two instructions. So the IFID pipeline register is frozen, the program counter value is frozen, and the control signals are made 0. And this disables the current instruction, and also this ensures that you repeat the same process in the next cycle. So I'm going to stop over here. I have discussed about the data hazards and this, and I have left many exercises for you people to do, because this is a master's or a graduate level course. So I'm not going to go into detail. I go into detail in the undergraduate level course, where I describe to my students how do we get these equations. And for a master level student, I just give an example to go through the book yourself and do it, because you are more learned students and you can do that yourself as well. Okay, so I'm going to stop over here, and all of this till this lecture is part of the midterm. Now there is an interesting thing that has happened, and that is that our university is going to open from the second week of September. That is actually the 17th of September, I think so. Yeah. So or 15th of September, I'm not sure about that. But that would be notified. But what we had planned was we wanted the the test, the midterm, to be an online midterm, and we planned it for a Sunday, and that Sunday was the first week of September. That happens to be 6th of September, and yeah, let's see. So if that is the case, then we can have it on online, or we can delay it for one more week, and you people come to the campus, and we can have a proper midterm. Yeah, what do you say?
So the proper midterm will be preferable at the university.
Okay, Iqbal Aziz says a proper midterm would be better. What about others?
Sir, I haven't heard about the notification. You earlier discussed about it.
One at a time. So, Mohammed Imtiaz, what are you saying? You haven't
Sir,
heard
I
about
haven't heard about your information.
what I'm saying. Yeah,
Said
what I'm saying is our undergraduate exams are going to start from 17th of September, and they are going to be physical exams. The students are going to come to the campus, and the schedules have been prepared for that. Subject to the notification of government, but the government is expected to open the universities from 15th of September, right? And if that is the case, is it better for us to delay the midterm by one more week, or do you want that midterm to happen on 6th September?
Sir, things are not clear yet, so it would be better that we should conduct this midterm online. And
Yeah, okay, I agree with you,
online, sir.
Yasir.
I go for online, sir.
Yeah, I agree with you, Yasir and Imtiaz, that things are not clear because maybe if something happened in the first week of September, and then it would be too late to organize. And so I'll keep the midterm online. So online means open book, and then there would be obviously some difficult exercises, or maybe something new for you, because hazard detection unit, or maybe something that I have not covered over here, like conditions for detecting the MEMWB to memory hazards. So I can ask that also in the midterm, right? So I'll keep it on 6th, inshallah, right? I'm going to tell you about the time, but it would be in the morning, not in the evening, because Sunday. So it would be something like 10 to 12, right, in the morning. On Sunday, Saturday, I'm not going to conduct on Saturday because some of you are going on job, and I don't want to keep it on working days, because it gets a little difficult for you people to get to conduct a midterm on a working day on evening, right? So anything that we have discussed up till this point is part of the midterm, and we are going to take the midterm online on 6th September, inshallah. Okay. Okay.
Okay, sir.
Thank you. So I'm going to stop over here.
Fine, sir.
If there are any other questions, you can ask me in the next class as well. So our next class, inshallah, will be on next Thursday. Okay.
okay, sir.
Okay. Take care. Allah Hafiz.
Okay,
Professor.
sir.